Okay, for question 20, this question is about benzene and some of its compounds. Benzene reacts with bromine in the presence of iron 3 bromide catalyst to form bromobenzene. Okay, draw the mechanism for this reaction, including the formation of electrophile. Okay, it's very easy. It shall be very easy to you too. FeBr with 3 reacted with Br molecules. Okay, so this will form FeBr for negative plus the electrophile Br positive. Then the ring that is rich with electrons, it donates 2 electrons for Br, and this will form the intermediate, which is like that. Part of the ring was placed, and here we have it. Now there is an arrow there which retain you back to the ring. Complete ring now, where Br is formed and plus H plus. That's the mechanism. Now, the position of Br is not like that. So if you rotate it, it will be like it. Don't worry. So it's completely correct. Let me tell you where are the marks there. I will tell you that. Look, 4 marks. 1 mark for this. 1. That's 1. 1 mark for the arrow that comes to draw this. Then 1 arrow here, the pole and the shape of the intermediate and the products. Here you have 2 marks for this. Okay. Now, the next idea is take care. There is a star there. It's asterisk question. Compare the contrast and contrast the reaction of benzene with bromine with the reaction of cyclohexene with bromine and of phenol with bromine. Includes the reason for any differences. Details mechanism for these reactions are not required. Now, we can summarize, or we can write. We should write in details because, look, he gave you 2 pages to write. So we can write in details about this. Can see. The first idea is, first he wants you to react phenol, cyclohexene, and phenol with bromine, compared and contrast the reaction benzene with bromine, phenol, and cyclohexene. Okay, now we can start within the benzene ring. Okay, the benzene ring. The first thing, or we can start within the cyclohexene. You can see cyclohexene reacts or undergoes the addition reaction, since we have carbon-carbon double bond, but benzene or phenol, they undergo substitution reactions. This is done from the mechanism. The second point is the cyclohexene and phenol reactions are done at they react with PR2, which is aqueous solution, under standard conditions or without catalyst. And benzene, while benzene needs the Friedel-Crafts or FeBr3 catalyst, or what is known as Friedel-Crafts catalyst. Though the benzene delocalized electrons and the reaction has high activation energy, while in phenol the delocalized electrons shared with the two electrons which they react. So where you have, so you can say that benzene delocalized electrons, in benzene we have the delocalization of electrons, which makes them kinetically stable. Take care that you have to use the combined sentences there. That's why I wrote them. And we have a lot of the benzene. Okay, there. Okay. Now, another one or another idea is that phenol delocalized electrons or phenol in phenol, that's the structure of phenol, where the two electrons are sharing the delocalization. So in phenol, the lone pair of oxygen in OH group share the ring delocalization of electrons, and this makes the more preferred to the electrophilic addition, yes, to the electrophilic, no, to the electrophilic substitution, to the electrophilic attack, not electrophilic addition. In benzene, it is kind of substitution to electrophilic. We can write it to electrophilic attack. Okay. And another thing, why it's kinetically stable for the carbon-carbon double bond in hexene, it's localized, so, or in cyclohexene, you are talking about this structure. So in cyclohexene, they are localized electrons. So it's more kinetically stable, localized electrons around or by bonds, and they are more fixed, more dense, or makes the electrons more preferred to electrophilic attack. Okay, like that, we give all the reasons which they present, and you will cover all points which they are needed for this kind of explanation. Next question, you will devise a synthesis to convert the bromobenzene into benzamide, and here we have long equation, includes the reagents, conditions, and the structure of the intermediate. Now, here, first part is to convert benzene into, or bromobenzene to something. So what we can do is the first reagent is magnesium, step 1. Step 1 is magnesium in dry ether. This will react with the bromobenzene, and this will form, if you react this with Mg in dry ether, this will give you this one, which is Mg Br. The next step is the Mg, sorry, step 2, the product from the first step, MgBr, was reacted with CO2 gas in then hydrolysis. This will give us with HC with an acid or dilute acid. This will give us the carboxylic acid, which is, yes, COOH. Now, did we prepare what is, no. After that, you can't react the benzoic acid directly with amine. You shall convert it into acyl chloride. So step 3, for this reaction, you will react this one with PCl5 or with something else plus PCl5. This will produce the C double bond O Cl, okay, and the continuity of the reaction. Then after that, you will convert this by reacting it with ammonia, the last step. Step 4, you will convert this plus ammonia, sealed container. This will give us the product, CO and H2 plus Cl. So it's misty fume which is produced. Then you will find that the product, which is benzenamide, was formed in the reaction. So that's the demanded one, sorry, that's the demanded organic product, which is benzenamide. Now, for part C, semi-aromatic polyamide have high melting temperature, high strength and rigidity, and are resistant to the chemical attack, so have many applications in engineering. Draw the repeated unit of the polyamide formed from the monomer or the monomers shown. Okay, it's very easy. You will combine the two monomers with each other. So you will see that this one was cancelled and here one hydrogen was removed. So you will discover something like that. CH2 by 6 in the middle. Here we have N, that's the unit, and then we have here N, okay, so then C double bond O, okay, then the benzene ring, and C double bond O, you will see that's the repeated unit for the structure, which is polyamide. it's polyamide 1. Okay. Same way, the polyamides have a higher melting temperature than polyalkene. Okay, since we have hydrogen bond, so this means that much more energy was needed, and it is stronger than the London force of it. Okay, here you shall talk about the bonds. So hydrogen bond or hydrogen bonding and London forces exists in polyamide compared to polyalkene, which has only London forces between its particle. So more energy is needed for stronger hydrogen bonds to compare to London forces. Like that, we finished section B. You can follow up more videos to complete the next section in October 2023 paper, Unit 5. Thank you for good listening. Thank you very much.